the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students going through coordinate systems, which involves a lot of change of coordinates between vector spaces. So you start with an abstract vector space maybe, and you're able to find the B coordinate vector for a given vector in that abstract vector space. So you can represent it in Rn. This video is going to focus solely on changes of coordinates between bases in Rn. So from Rn to Rn. So we're letting go of abstract vector spaces for the time being, just for this video, because, well, all the theory here only really applies to changes from Rn to Rn. Let's define a change of coordinates matrix here. Suppose that we have a set of vectors which form a basis for Rn. And also suppose we have a vector x that's also from Rn. Therefore, x obviously can be written as a linear combination of these basis vectors right here. And the weights of that linear combination will be listed in the B coordinate vector right here. That's what I'm saying is the coordinate mapping of x determined by B. Then the matrix P sub B, which is the matrix of all the basis vectors that we have for our current basis B, is called the change of coordinate matrix from B to the standard basis in Rn. There's not much else I need to say there. I'm just defining what the matrix is, which contains all the basis vectors from that set. And we're going to call that the change of coordinates matrix. And by the way, it changes the coordinates of a vector that's written in terms of the basis B to the coordinates of a vector via the standard basis in Rn. Now that's a mouthful, but before we can actually go into an example, there is actually a theorem we need to talk about. And note, the following theorem is a combination of three theorems. The three theorems are the two statements shown here that the vector x is just the change of coordinates matrix times the B coordinate vector of x. The second theorem is that the B coordinate vector of x is the inverse of the change of coordinates matrix times x. And remember, x is in terms of the standard basis here. And the third hidden theorem is that P is invertible, that the change of coordinates matrix has an inverse, but that is implied by this theorem. I just didn't want to write down 3 pages of theorems if I can encapsulate them in a single page. Now, rather than prove these right now, I will, but rather than start with a proof, let's actually just see everything in an example. Consider the basis from R cubed. It's 123, 014, 560. That's going to be our basis for R cubed. We're going to start by finding the change of coordinates matrix from B to R cubed. And as was stated on the definition page, this is literally just the matrix whose columns are these vectors from the basis. So part A is actually done. There's nothing else that I need to do there. Part B is asking, suppose x is found by moving 3 units in the B sub 1 direction and -2 units in the B sub 2 direction. Find both the coordinate vector of x in terms of the basis B and also find the actual vector x. And this is just a shout back to how we started all of this material, where somebody has given us a brand new basis. This is in R squared, our current problem's in R cubed, but still the same thing applies. Somebody hands us a brand new basis or set of basis vectors, B1 and B2 in this case, and we want to arrive at this vector x. How do we get there using these basis vectors? Well, in this picture, I go back 2 steps in the B1 direction and go forward 1 step in the B2 direction, and I will arrive at this vector x, which is, by the way, 1, 2. So using that information, we know that x is being found by moving 3 units in the B1 direction and -2 units in the B2 direction. By the way, 0 units in the B3 direction. So if I were to write this vector equation as a matrix equation, I'd probably want to stick on here that I have no move in the B sub 3 direction, because then it's very obvious that x is just equal to the change of coordinates matrix, which is basically our matrix full of the basis vectors, times the vector 3, -2, 0. And that vector 3, -2, 0 is actually the coordinates of this vector x in terms of the basis b, written like this. And this kind of works well with the theorem we just saw, this guy right here. X is equal to the change of coordinates matrix times the b coordinate vector. So we've already found the b coordinate vector. Now I just need to find x, and that's just multiplying the matrix times this vector here. So let's go ahead and do that. And we get that the vector x, the vector with regards to the standard basis, is 3, 4, 1 over 3 units in the x sub 1 direction, 4 units in the x sub 2 direction, and 1 unit in the x sub 3 direction. And again, that's with regards to the standard basis. With regards to the basis b, the move would be 3 units in this direction, -2 units in that direction, and no units in this direction. So that actually answers part B. We found the b coordinate vector for x and x itself. Finally, part C, we're just asked to compute the inverse of the change of coordinates matrix and use it to compute the b coordinate vector of x equals x sub 1, x sub 2, x sub 3. Going back to the theorem here, the b coordinate vector can be computed using the inverse of the change of coordinates matrix by just finding the inverse first and then multiplying that by x. Remember, x in our case we're just considering to be an arbitrary x, so it's x1, x2, x3. So we know what the change of coordinates matrix is. Now let's go ahead and find its inverse. Okay, so we found our inverse for our change of coordinates matrix. It's this guy right here. We'll take that and multiply it by the vector x to find out what the b coordinate vector of x is. And there we have it. If we knew what x1, x2, and x3 were, we could then plug them in and we would have the actual b coordinate vector for x. Mechanically, these problems generally are not much of an issue. Most students are pretty good with this stuff. However, it's remembering the formulas, these guys right here, that's critically important. So let's go ahead and prove this theorem. Since we're at the end of this video, it'd be nice to kind of have this theorem proved. So let's go ahead and do it. I'll start with this right here, which I'll call 1. And I should mention before I even begin where these vectors come from. So let x be from Rn, P sub b be a matrix full of the basis vectors for our vector space Rn, and let x sub b be the b coordinate vector of x. Well, by definition, the entries in x sub b are the weights of each of the corresponding basis vectors that will yield the vector x. That is, this linear combination of the basis vectors is designed such that it will yield the vector x. So that actually proves step 1, or problem 1, whatever you want. The next thing I actually want to prove is the one that's not written here, that the change of coordinates matrix is invertible. And that's pretty quick to prove. Since P sub b consists only of basis vectors, the columns must be linearly independent. If they're not, then they can't be a basis for the vector space Rn. Moreover, there has to be n of them, and each of them must have n elements. Thus, P sub b is a square n by n matrix. By the invertible matrix theorem, you have a square matrix with linearly independent columns. That means that matrix is invertible. So that proves 1 and 2, and then 3 just falls out by multiplying both sides of 1 on the left by P sub b inverse. So that actually proves everything that we wanted to prove, and that finishes out this video. Not much to it, right? Really very fast. Once you know these two formulas right here, x is equal to the change of coordinates matrix times the b coordinate vector x, then you have everything else really to do problems like this right here. In essence, working from Rn to Rn is usually not an issue. All right, I hope that this video helps you out in some small way, and I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.